In this lesson, we're going to be learning about a brand new function called a logarithmic function. And the way that we're going to start this off is by revisiting exponential functions. So remember that exponential functions are one-to-one, which means that every output that we get only comes from one input. So we could see that graphically by recognizing that this passes the horizontal line test. Now you might remember as well that every one-to-one function will have an inverse function. So that would mean that b to the power of x, regardless of what the base is, will have an inverse. The question is, what is it? So remember that inverses are reflections over the line y equals x. So if we were to fold this over the line y equals x, recognizing that all y values must be positive, now we realize that all x values would have to be positive. And you could see that this would be the reflection or the mirror image over the line y equals x. So if the blue function is y equals b to the power of x, then the inverse function swaps the x and y values, giving me x equals b to the y. So this red curve is the inverse function of the exponential. The problem is we don't have a way to solve for y. There's no way for us yet in order to get that y out of the exponent. But one thing to recognize about y is that it's the power to which we have to raise b in order to get x back again. So essentially, y is going to be the power while x is the final result. Right? But unfortunately, we don't have a method to get it out yet. So we're going to have to take a look at it from another perspective. So taking a look at this graph of y equals 2 to the power of x, let's keep in mind what this actually represents. This means that if we were to pick some x value of 2, then the output would be 4. And we can see that graphically because the x coordinate of 2 maps to a y coordinate of 4. Now, if we take a look at 2 to the power of 3 equals 8, that would mean that we would have to plug in 3. And if we do so, we would get an answer of 8. Now I'd like to ask a question. How do we get 6? What power would we raise 2 to the power of in order to get 6? Well, we know that there has to be some value. So if we think about it, maybe it's 2.5. Okay, but if we punch that into our calculator, 2 to the power of 2.5 is not the answer. Because notice that at 6, we're going to get this particular result. And if we map that down to the x-axis, it looks like it's a little above 2.5. So punching this into our calculator gives us an answer of 5.65 or so, which is too small. So maybe the answer is 2.6. But if we use our calculator again, now we see that 2 to the power of 2.6 is 6.06. It's not exactly 6. So 2.6 is too high of an exponent. So one thing to recognize here is that exponents do not need to be whole numbers like 2 or 3. We could get exponents that are going to be decimal values. So if we pick something maybe between 2.5 and 2.6, maybe we pick 2.58. And notice that, well, too small, just a little too small. Notice that I was supposed to get an answer of 6, but this is 5.979. So it's a little bigger than 2.58. So maybe we try 2.585. And notice that that's about 6.00015. Again, it's too big, but we're going to say that that's close enough. And if x is approximately 2.585, then we know that 2 to the power of x will be 6. So notice that what we're trying to get at here is that 2.585 is the power that we need to raise 2 to the power of in order to get 6. So notice that what our objective is for an inverse function is what if we start with the output and we want to now go backwards to find what the exponent is. This is what we define as a logarithm. A logarithm is simply the inverse of an exponential. So what this tells us is that if we have the standard function f of x equals b to the x, that's our exponential function, then we can call our inverse of f of x log base b of x. Log is nothing more than a symbol that's just designating that it's the inverse of an exponential function. So let's take a look at a really important relationship then between exponentials and logarithms. So in this formula, if we say that b has to be positive because it's the base, and we stated that for exponential functions as well. And then we also stated that the base could never be 1. So if we have a positive base that's not equal to 1, and all of the x coordinates are positive, then we can rewrite x equals b to the y as y equals log base b of x. So let's think about what this actually is saying. B is the base of this exponential. So b then becomes the base of this logarithm. Logarithms always solve for exponents. So we should realize that over here, the y value is the exponent. And now when we convert to a different form, the logarithm is equal to the exponent. X is the answer that we get after raising b to a power. So x is the value that goes inside of the logarithm. So notice that the base is the same here. The exponent becomes the answer for the logarithm, and the x value is referred to as the argument. So let's take a look at an example that actually demonstrates this. So your success here, as I mentioned down below, really depends on your being able to convert between a logarithm form and an exponential form. So recognize here that the base and the argument must both be positive. But let's think about why the argument, the x value, has to be positive. Why does the quantity inside of a logarithm need to be positive? Well, remember how exponentials work. If I raise any number to a power, whether that power is negative or 0 or positive, the answer that I get is always positive. So when I change the form, that x value is now on the inside of the logarithm, and therefore that x value, in addition to the base, always must be positive. So the way we read this is log base b of x. All right, so let's take a look at a couple of examples here. So first of all, we have a couple of logarithms, and we have a couple of exponentials, and we want to change the form. Well, let's keep in mind what we do for log base 2 of 16 equals 4. 2 is the base. Remember that logarithms solve for exponents. So 4 is the exponent of 2. 16 is the answer that we get when we raise 2 to the power of 4. So 2 to the power of 4 is equal to 16. So now let's start with this next exponential. If this is an exponential, we recognize that 5 is the base, so we start by writing log base 5. Now -3 is the exponent. So remember that exponents go on the other side of the equal sign, because notice that logarithms solve for exponents. So that would mean that log base 5 of 1 over 125 is equal to the exponent of -3. So what if we had a logarithm log base 4 of 4 equals 1? Let's think about what that means. It's telling us that 4 is the base and 1 is the exponent. So if I raise 4 to the power of 1, my answer is 4, which turns out to be the argument of the logarithm. What about this exponential? Here we see the base is 6, so we know we'll have log base 6, but the exponent is 0. So I know that the logarithm has to equal 0, so log base 6 of 1 is equal to the exponent of 0. This is a very important part of the process of being able to convert between exponentials and logarithms, so really make sure that you practice this definition in order to be successful with logarithms. So let's take a look at this example of how to maybe solve this basic logarithm equation. We're trying to figure out what base do we have to put in here so that when I raise it to the power of 2, I get an answer of 25. Well, notice that 2 is the exponent to which x is raised in order to get 25. So by using that definition, we could just simply rewrite this as an exponential form. So now I realize that if x squared is equal to 25, then that must mean that x is either positive or negative 5. But keep in mind that x is a base in this equation, and bases must be positive. So since the base must be positive, the answer for x is 5. Let's try a different one. If I want to solve this logarithmic equation, now we're saying that the logarithm has a base of 1/2. The logarithm solves for an exponent, so x is the exponent of 1/2. So what is the exponent to which 1/2 is raised in order to get 1/16? So by using the definition again, we could just simply say that log base 1/2 of 1/16 equals x could be rewritten as 1/2 to the power of x is 1/16. And so if we think through that, that would just mean that 1/2 to the power of x could be rewritten as 1/2 to the 4th, or 1 to the 4th over 2 to the 4th. So now that the denominators have the same base, you should be able to recognize that 1/2 to the power of x is equal to 1/16, which is 1/2 to the power of 4. And therefore, the x value must be 4. So notice that what we're dealing with here is showing that logarithms solve for exponents. Therefore, if I ask you for a logarithm of a number, the answer you give me should be an exponent. So what if I wanted to find log base 49 of 7? Well, logarithms are exponents. So I'm saying that 49 is the base, to which we have to raise to some power which we don't know. So let's just write that as 49 to the power of x should become 7. Now it seems a little peculiar because x, or 49, is larger than 7. So how do I raise to a power that's larger, or I'm sorry, how do I raise 49 to a power and get a smaller number? Well, the easiest way to do this is to get the bases on both sides to be the same. So you could see that 49 is the same as 7 to the power of 2. So I could rewrite this as 7 to the 2x power is equal to 7 to the first power. Well, if the bases are the same on both sides, then that must imply that the exponents are the same. And therefore 2x equals 1 implies that x is equal to 1/2. So the exponent that I have to raise 49 to the power of in order to get 7 is 1/2. So notice that if we were to take a look at the decimal system that we use is a base 10 number system. What that means is that we have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, and we could create any number, any decimal number, any whole number, just using those 10 symbols. So if we were to look at some number, for instance, 4,783.29 or 29 hundredths, we could actually break this apart into each of their individual digits. So that the 4 is in the thousandth spot, so I could think of that as 4,000. 7 is on the hundred spot, so I could think of adding 700, then adding an extra 80, adding an extra 3, adding an extra 2/10, and adding an extra 9 hundredths. And if you think about that now I can rewrite each of these terms as 4 times a power of 10, plus 7 times another power of 10, plus 8 times another power of 10. And so notice that these are base 10 number systems. These are very common in the way that we describe numbers. And so if we could rewrite each of these numbers as a value times 10 to some power, we could actually see the relationship between the base 10 number system and base 10 logarithms. We refer to logarithms that have a base of 10 as the common logarithm because we actually deal with base 10 on a regular basis in our counting numbers. So if I ever see y equals log base 10 of x, that could be rewritten as simply y equals log x so that you don't see a number below the logarithm. So if there's ever a logarithm without a base, we have to imply that the base is 10. So let's do some conversions for these problems. So if I have log 1000 equals 3, I have to recognize that logarithms can be turned into exponentials. So I need the base, but I got to remember that the base is 10. So I could say that 10 is the base, logarithms are exponents, so 3 is the exponent on 10. So I could rewrite this as 10 to the third power equals 1000, which is equivalent to log 1000 equals 3. If I want to rewrite 10 to the power of 1 equals 10, then I see that 10 is the base. So I could write this as log base 10. But remember that exponents are logarithms. So the logarithm has to be equal to 1, and therefore I know that this is log base 10 of 10 equals 1. But notice that we never wrote the base 10 because it's not necessary if it's a common logarithm. And lastly, for here, if I have log 1 equals 0, the base is still 10, but logarithms are exponents. So I could rewrite this as 10 to the power of 0 equals 1. Let's take a look at some features of the graph of this new parent function called log base b of x. Now that base could be anything we want it to be. It could be a base of 2 or 3 or 5 or 10 or e. It could be anything. But let's see what's true about all logarithmic functions. First of all, the base must be positive, just like the base of an exponential. Next, if we take a look at the domain of this function, remember the domain are the x values I can plug in. Well, the only x values, the inputs that I'm allowed to plug in here, is any number that's on the right side of the y-axis. I don't see the graph on the left side of the y-axis, and therefore I could only plug in values that are positive. So the domain is 0 to infinity, not including 0. Which makes sense because the interval 0 to infinity implies it's all positive values. All right. If I now take a look at the range is all the y values that I get out. Well, notice that the graph goes down to negative infinity, and it just continues to increase to positive infinity. So the range is negative infinity to infinity, which also makes sense because logarithms are exponents. Logarithms solve for exponents, so the y value could be anything we want. We can get any value as an exponent. As opposed to the argument, arguments must be positive, since b to any power is always positive. Now, if we recognize that b is greater than 1, then the graph of f is going to be increasing. So if I have 2, a base of 2 or a base of 3, try to relate this to an exponential, that would end up increasing as well. But if the b value is a fraction, now the logarithm is going to be decreasing. So the y-axis will be a vertical asymptote for both graphs. But if it's an increasing function, the graph will go down to negative infinity. And if it's a decreasing function, then the graph will approach the asymptote going up to positive infinity. Now notice that if exponential functions always had a y-intercept at 0, 1, then by flipping the x and y values, logarithms should always have an x-intercept at 1, 0. And we can see why that would be true, because if I plug in 1 up to our logarithm here, then I'd be saying log base b of 1 is equal to some value. This would imply that b to some power has to become 1. And the only power that I could raise to get 1 is 0. Now f of x will always pass through the point b1 as well, which means I would go out to b on our x-axis and up to 1 on our y-axis. And again, the reason for this is that if I plug in b to the argument, then the way to make this equation true is for the exponent to be 1, because b to the power of 1 gives itself. Finally, the y-axis is always going to be our vertical asymptote, as we saw for either an increasing or a decreasing function. And that's because the inputs can never be 0 and it can never be negative. So let's go ahead and take a look at a few specific graphs of logarithms. So if I graph log base 2 of x, or log base 3 of x, or log base 5 of x, I should realize one similarity, and that's that the x-intercept is always 1, 0. But now I'd like to plug in a value of x that's going to give me a nice y value. So notice in the first one, I would like to make a y value of 1, or an exponent of 1, so I can always use the value that's going to make the base of the logarithm equal the argument. So I can see that log base 2 of 2 should be 1, so plugging in 2 is going to give me an answer of 1. By knowing the shape of logarithms, I can increase through those 2 points, and that gives me log base 2 of x. If I try to graph log base 3 of x now, it's still going to go through the point 1, 0, but now I should realize that plugging in 3 will give me an answer of 1, because log base 3 of 3 equals 1. So I can plot my second point at 3, 1, and notice that that's now going to be a shallower graph. But what about log base 5 of x? Notice that I would have to plug in 5 now in order to get an answer of 1. That would mean I'd have to go all the way out to x equals 5 in order to get the same output of 1. And notice that that's going to cause the graph to be even shallower. So logarithms are always going to look like the inverses of exponentials, where the vertical asymptote is the y-axis. The 2 points that you're going to plot are all based off of what the 2 points you'll plot for the parent function are all based off of what the base is. So now let's apply some transformations, just like any of our prior parent functions, in order to graph the function log base 2 of x plus 1 minus 1. So the first thing to recognize is that the parent function is log base 2 of x. So I would plot the point 1, 0, and I would plot the point 2, 1. And now that this is our graph, I need to realize that x plus 1 means to move left 1. Subtracting 1 from the end of a function means to move down 1. So the same types of transformations apply. So I'm going to move each point left 1 and down 1, left 1 and down 1. And so both of those blue points have now become the red points, and I now need to connect the dots to create the same shape. The problem is that the y-axis was a line that acted as the vertical asymptote. But now if I move it left 1, I have no vertical line to get close to. So if I ever have a horizontal shift on a logarithm, that means that it's going to move that vertical asymptote. So I have to draw the vertical dotted line here to show that that's the limiting line or the asymptote. And now I have something to get close to. So the graphs of logarithms are going to work exactly the same as the graphs of any other function. It's just now going to be a brand new shape. I'd now like to take a look at a special type of logarithm referred to as a natural logarithm. We refer to this logarithm as log base e. So when we look at a natural logarithm, or in other words, ln of x, we imply that the base must be e. And remember that e is about 2.718. So this natural logarithm is going to be very closely related to log base 2 of x and log base 3 of x. So let's just go ahead and start over and recognize that we still want to get those values of 1. So I would recognize that log base 2 of x would go through the other point 2, 1. And we could see that it's the inverse of 2 to the power of x. And so if I were to reflect over the line y equals x, that's why this blue graph is the shape of this logarithm. So remember that logarithms are always inverses of 2 to the x. So now let's look at 3 to the x. Well, remember that plugging in 3, log base 3 of 3, is what's going to give us a value of 1. So now we realize that this is our next point, and that's log base 3 of x. Well, remember that that's the inverse of 3 to the x. 3 to the x was a steeper exponential, so when I reflect that, it becomes a shallower logarithm. But now let's take a look at ln of x. ln of x is simply a logarithm with a base of e, but we don't write log base e of x. What we write instead is ln, Latin for Logarithmus Naturalis, natural logarithm. Well, remember, if I graph e to the power of x, e is about 2.718, so I know that e is going to be giving me a value of 1. Remember that e to the power of x was a graph that was in between 2 to the x and 3 to the x. So it would imply that the natural log of x should also be a logarithm somewhere between log base 2 of x and log base 3 of x. So the 2 points that we plot will be 1, 0, and e, 1. Let's try to evaluate a few expressions involving the natural logarithm. Let's say we want to find the natural log of 1. Well, remember the base is e. So we're saying e has to be raised to some power to give me an answer of 1. So what power do we raise e to in order to get 1? Obviously, the value would have to be 0. So ln of 1 is equal to 0. How about ln of e? Well, remember the base is e, even though we don't see it. So this is saying e raised to what power gives me e again. E to what power is going to get me right back to e. Well, we should see that that power would have to be 1, which is why the natural log of e is equal to 1. What about ln of e to the power of 3? What is this logarithm equal to? Well, this is saying that e is the base. Now notice, we're not referring to this e. We're referring to the base of the logarithm, which is blank. We don't see it, because when we see the natural log, or ln, we imply that the base is e. The argument is e to the third power. So we're seeing e raised to what power gives e cubed? Well, in order to make both sides equal, that power must be 3. Why don't we take a look at ln of 1 over e squared? This is saying that e raised to what power gives me the argument of 1 over e squared? Or in other words, e raised to what power gives me 1 over e squared? Well, it's still a little tough to see because I can't really make both sides look the same. But what if I rewrite 1 over e squared as e to the negative 2 power? Now I can realize that this is saying e to what power gives e to the negative 2. And now, since I see the base of e on both sides, that must imply that the y value is negative 2. And therefore, ln of 1 over e squared is negative 2. So the most important thing to recognize about logarithms is that logarithms are exponents. When I give an answer for a logarithm, my answer is an exponent that gives the result of the argument. So make sure to always know how to change back and forth in between exponential form and logarithmic form in order to assure success.